Okay, my friends, this is a shocking coincidence. I just put up a video about fission and fusion and how we can get free electrical energy right now because we can create fission and fusion. Now, she's saying, listen to what she has to say. She's very good, Sabine Hassenfelder. And here she goes. All right. Now, she's going to be talking about nuclear fusion and how it could save the world. And they are also talking about it in all the other agencies, but nobody seems to know how to do it, and I think I might.
Nuclear fusion is a great idea in principle. In principle, it could solve the energy worries of the world beautifully. The problem is that whenever we've tried, getting nuclear fusion to work takes up more energy than it creates. But a team from Japan and the United States just got us a bit closer to our dream of a perfectly clean source of energy. They recently succeeded in controlling nuclear plasma in a stellarator by creating a digital twin. What's a stellarator? What's a digital twin? And what?
All right, let me just show you what they're trying to do. And they're having all kinds of problems with it. And you're not going to be able to carry these things around. All right, these are big devices, and they're not stable, and they're just trying to learn how to do it, and they're wrapping all kinds of magnetic confinements in here to try to keep these flowing correctly. Listen to this.
That allows the device to be smaller and should also make it harder for the plasma to escape, thereby increasing efficiency. The biggest existing one is Wendelstein 7X in Greifswald, Germany. The problem is these stellarators are much more difficult to build than tokamaks, and they're also more difficult to model, so they haven't been studied all that much. Some companies use entirely different approaches. Notably, there's what's called inertial confinement. Inertial confinement basically means you shoot at a fuel pellet in the hope that it blows up. All
right, let me just explain to you what fusion really represents to them. I can show you fusion, and it's not what they do. What they're doing is taking what they call fuel pellets. They're little particles that if you heat them up so hot, they'll just give off a ton of energy as they fuse together. But you have to put more energy into it to make it fuse. You're never going to get even. Just like she said, they've never been able to even get even. Because all they're doing is putting energy in to get energy out. That's all. It's crazy. It's crazy. We're putting energy through a venturi and getting the particles to come out in these huge arrays of raw energy. All right, check this out. This is some serious amount of...
Currently the largest tokamak in the world, and another tokamak that's currently the biggest in the United States. They taught it to recognize data patterns.
All right, this is crazy. I'm showing you some... Oh my God. Okay, I'm just going to go right to the heart of the matter. We accelerated light, and we actually created fission, and then it came back together as fusion. This is light that is not accelerated. Well, it's just starting to accelerate. But there's a particle in here, and it has a big field surrounding it. So there's a little tiny particle and a big magnetic field, and it pushes everybody else's magnetic field, so everybody glows, and this one glows the most because it's pushing. All right? But all these little particles here are other fields of other gases that are being impacted by this magnetic field. And it's starting to pull forward. And now it's going to go into full acceleration, which is right here. So remember, it was back here. Now it's in full acceleration. And not only that, the particle that was back in here, which I'll show you in a second, is now manifesting itself and pulling itself right out of its magnetic wave, just like breaking a sound barrier. And here it explodes and creates fission, where the black gets away from the white, show you in a second, and here it comes back together as fusion. So what they're doing is something different. They want to take big particles, big chunks like this, actual atoms, and slam them together and have them give off a bunch of extra particles. But these are the extra particles they're looking to give off. We just squirted it through light. So we didn't have to work with this, which is dangerous. These are dangerous. We don't have any danger here at all. We're working with light. So it squirted through. Well, what happened at the Venturi? Here's what happened. Right here, the black particles separated from the white. I'll show you, well, let me show you they're attacked together so there's no question. Here's where they came through. That's the particle. The black and the white attaches together like this. That's the strong nuclear force. This is subnuclear. This is way down. This is one of these. All right, actually it's two of these, because they're dipoles, little tiny dipoles, positive and the negative together. But when you take two of them together, it makes a photon. A photon will bounce because now it has a full magnetic field around it. The whole thing is a ball around it. It's just like a basketball. Now, you have only one of these, and you have a black and a white. You just have a field here, and the other part, this is going to want to bounce away from something or attach to something. Depends on what it's coming up to, which means heat goes in, cold, it comes back out. If something wants an extra electron, it's available. But normally, free electrons are going to be heat, basically. And then, of course, you can have static electricity and lightning and all that business. Those are free electrons in mass. All right, you're going to have to come up and look at my last video to see all the details. But this is what they're saying from Jefferson Labs and all of them. They say that it's made of quarks inside the proton. It's not. It's made of 1,823 dipoles. And they push the black stuff to the center. I have something here that is my stuff. All right, give me a second to lock in here. There it is. This is dipole electron flood theory. And you have a black and a white of everything. So at 1823, you have 1,823 dipoles. But the black can be pushed to the center, and the white coats everything. That's how it works. Now, it could be this way, or it could be layered. This is the layered one. All right, where it's still got a black core, but then it goes out in a layer and another layer and another layer of the black. The other one has only all the black in the center, and then the other layers are, each layer is a more strong layer. The ones, the blue ones, are just right against the black ones. They're as tight as they can possibly be. They don't want to leave. Those things, when they go off, they go off. And I can show you that. They're very, very high energy. Blue is just extremely high energy. Green, a little less, and red is kind of weak. And I'm going to show you those right now. All right, look at this now. This is what they do at all the particle colliders. They take big chunks like this, they smash them together, and they get all of this kind of stuff. But we started with these little bitty particles. So we never have to deal with any of that stuff. All right, and then they have debris, which is in big chunks. If that hits you, that kill you. That's why the nuclear radiation is so damaging, because they're big, big particles, and they want to either incorporate into something which is invasive, or they want to explode, and then that's also invasive because it's a big particle slamming into your body. It can cause DNA damage, cellular, just all kinds of stuff. See, the whole idea is they want to knock off free electrons and then capture them. They're actually shooting them off as making them into heat. We are shooting them off, and we should be able to capture them in a solar collector here. They're just moving forward. And that's where the black and the white separate. So this is fission, and then that's fusion. Now, when they do fusion, like I said, they take two big chunks together here, and they just heat them up so hot that they sort of melt together. Basically, that's all they're doing. So they're putting more energy in than they're going to ever get out. It's never going to work. We didn't put any energy in whatsoever. We shot the laser through the Venturi, which is so tiny here, and it's a restrictive Venturi. So only the particles that we want to allow to get through there can get through. And depending upon the construction of the Venturi, we can keep the black ones out. They're bigger and they're strong. They're fixed size. They're all the same size. Never going to be different. That one is exactly the same as that one. Exactly the same as this one. They're all the same. There's no big ones, no small ones. They're all the same. And they're the same in the red and the blue and the green. So you just saw them right here. They separated. Originally, they were together. Here's the stuff from Fermilab. They show the same particles, exactly identical. Look up, it's called What's the Point? Point particles. And here they are. Those are the ones we found. And so we started with light. They started with the big stuff. So that's all they could see is for 10, 15 years or whatever, they keep looking at this stuff and they say, we see the smallest ones we've ever found are these two. But we see them in light. And we can see that the white ones get bigger and smaller and the black ones do not change size. And we did separate them, which is fission or fusion. We accelerated them out. And this is what they look for. This is what they want. It's the sterile muon, the black ball, and they want the electron shower. Electron shower is literally 100% energy. It's 100% electrons. And they have no weight whatsoever. But they have all the energy. When you fill your car up with electricity, it's that you put in your car. That's exactly what you put in your car to fill it up. It doesn't add any weight whatsoever to your car. None, zero. You start with 4,000 pound car, fill it all the way up full with electricity, still weighs 4,000 pounds. Drive it around until it's empty, still weighs 4,000 pounds. Fill it back up, still weighs 4,000 pounds. This has no mass to speak of. It has no weight. The black is the dark matter. They say it makes up almost all the universe. Yes, it does, because they've never seen it before. It's attached to the white. But anytime you get into this size of materials, it's always coating the black. So we never see the black. The only reason we see the black is because it's sitting right on top of our white. That's the only reason you see it. Over in here, you don't see it. But here, you can just barely see it. It's still obscuring some of the white over here. But here, there's no black whatsoever. That's because we're not letting it come through the Venturi. It's not because it doesn't exist. It's just we kept it from going through the Venturi. And then, which is, anytime you break something apart, it's fission. You break something apart, it's fission. You put it back together, it's fusion. Now, for them, like I said, they wanted to make these two things join together, but all they did really doing is melting them. They're just melting them together. So they have to put more energy in to melt them, and they think they're doing something important. They're not. All right, I don't think I mentioned this yet. This is extremely fast blue, very, very fast. And you can't even tell there's two dipoles here until you get way out to here as it's slowing down. So we can slow light down, that's no problem whatsoever. And we can speed light up, that's no problem whatsoever. This is the green speeding up, the red speeding up. Now the red is weak though. The red has no power, well it has power, but it's not, well here's the red and the green together. You saw the blue would be like, we can't really work with the blue. The green and the red we can sort of see pretty good. And you see how powerful the green is, and then it reconcusses out here. And here's the red, just gets pushed out of the way. These are the same photons. You see the photons? Same photons, only they're green because they're spinning faster. And these are the neutrino values prior to becoming a photon. And the same thing with the red. The red has these neutrino values, see it? And then all of a sudden it becomes a photon just before it hits the Venturi. I believe I showed you most everything else in these Higgs fields. The Higgs fields come this way here, and Higgs fields show up right here. That's these. And that's as these little spritzes bang into the black particles, they just spin around and they do this. And what we're doing is very simple compared to what they're doing. They're trying to see if the standard model holds up, and it doesn't. It absolutely doesn't. They can't account for gravity. All the particles I'm showing you are made of these two particles. A black and a white and a black and a white. And they can get big and they can get small, just as I show you here. See the white ones bigger and smaller? They can squirt through the Venturi. But no, their normal thing is they're attached, and they say it takes a ton or more of energy, literally a ton, to pull them apart. And that's what electrical generation is. I have a generator, it's a good-sized generator. It runs my house if I run into trouble. But when I flip it on, the engine going, and I flip it on, it's, you really got to push some of it. You're ripping these suckers apart. To make that white go do some work, you got to put a lot of work in. That's what a generator is. That's what an engine is. All that stuff. You got to put a lot of work in. We didn't have to put any work in at all. We just said, you black particles, stay back. Let the white come through. And then what we should be able to do, and I don't see any reason why not, to do this, make a little device like this. A handheld thing, like a lunchbox. You carry it around, any kind of plug you want. Click anything you want for selective AC, DC, 50 cycles, 60 cycles, USB, anything you want. And inside of there, you should be able to have thousands, literally thousands of these lasers and the little tiny venturi and the receiver on the back side. And you want to harvest it just before it comes back to where it would normally reattach to the black. All right, so in this case, you'd have your laser up here shooting, your little venturis going here, and then you'd put your receiver just before it hits here, because the further out the cone is, the more energy you have. And that's what they say, and I believe that would be true, because the bigger the showers, the more energy. And there'll be some changes. There's going to be some changes to the atomic weights and all that business, and some differences in the standard model, and some changes in chemistry too. Chemistry's totally got a lot of work to do there because of all the isotopes and nucleophilic substitution and invasion that happens using enzymes and so forth. There's a lot to talk about there. Redshift, that doesn't work at all. Redshift is just light slowing down. That's why it's not necessarily the expansion of the universe. And everything is put around Einstein's rule that we have to go the same speed no matter where it is. It's absolutely wrong. It's totally 100% proven to be wrong right here in your face. If that's going the same speed, then I don't know what you're just not playing. You're just playing by a bad set of rules. You're just not being honest. If it's going the same speed as that, no, absolutely not. They're both light, no question whatsoever. That's acceleration, and there's no question whatsoever. This is slowing down. It's coming in hot, slowing down. Light is not. It was just wrong. Einstein was just totally wrong. And because of that, we've been stagnated for 100 years. And here it is right here, how we can get out of this. And for them to want to do all this fancy stuff because they're still trying to stay with the standard model, here it is right here. They're trying to continue on. Critical decision clears the way towards standard model test. Well, I showed you it doesn't work. And they can't account for gravity. They can't account for dark matter. They can't account for anything. And it's because they have to go with the universe is expanding because light must be being pulled away. Because all those things are just being pulled away, so it's shifting red. By the time we see it, it's all stretched out red. No, it's coming in fast like this, and it's just slowing down as it keeps banging through everything that's in space. And there is a ton of stuff in space. You want to see it? Sure you do. See, this is what space is like. You got to go through all these fields, and every one of those fields is bounce backs, and it makes you blink on and off the light as it comes through. Even Fermilab says that. Watch. You see that? I just showed you all the particles. They're exact same particles. They work exactly the same way. This is the fix. This has no weight whatsoever and all the energy. That has no energy to speak of, and it has all the weight. And then they talk about the standard model being all perfect. No, it doesn't work at all. And they talk about the quantum foam. Now, the quantum foam is another thing that they say right here. Empty space isn't empty. It's not. All the light is coming through there, all the particles, all the dust. And here's exactly what he says at Fermilab. He says, The foam on a head of a root beer is a complicated environment, bubbles appearing and dizzying display on and off changing. Empty space experiences similar activities. It's not empty. Subatomic particles, which is these particles I'm dealing with, these subatomic light particles. Subatomic particles winking in and out of existence. Why? Because another one comes in and bangs it out to it. It blink and it goes by, blink and it goes by, blink and it goes. So hitting and hitting and hitting and hitting and slowing down as you go through those fields. So it says empty space experiences a similar activity. Subatomic particles winking in and out of existence as they're being banged into and slowing down. These subatomic particles are real and have a measurable impact on our universe. I agree. Empty space is not empty. It isn't empty. As we come through that space, it slows everything down. You bang into those fields, it lights up. And it does, it absorbs some of the energy, and it goes, actually, see, you can see them coming out. They're very high energy early in there. Now, the same thing happens with light. As light comes through all of these other particles, it may bang into one, and another one, and another one. And as it does, it slows down. We're seeing light shifted to the red because it's just slowing down. And then the cosmic microwave background, which is this very slow, particles aren't even moving hardly. Those are just particles that just never hit anything enough to stick to it. They're just sort of floating around out there. That's the cosmic microwave background. All right, the other particles are streaming forward because they're being ejected from the stars and the sun and so forth. Look at this. This is amazing. I'm just getting ready to finish up, and this came in, so we're going to have to look into this. Here we go. Read more. This is about nuclear fusion, world record smashed and major achievement. They still didn't break even. I know they couldn't have broken even. You can't. Hold on, let me look through this. And here it is right here. They making a big deal like they're making a whole bunch of energy. This only lasted 5 seconds, first of all. And they say it created enough power for 41,000 homes for 5 seconds. Guess what they had to put into it to get it out? Inside the tokamak, this 0.1 milligrams each of deuterium and tritium, both isotopes of hydrogen, heated to temperatures 10 times hotter than the center of the sun to create plasma. Well, what if they just let the 10 times out come out? That would probably heat houses for 5 seconds too. And they you know, what they're doing is not, it's just not correct. Deuterium is freely available in seawater. Tritium can be harvested as a byproduct of nuclear fission. Well, we created, you know, light fission. All right, and then it comes back together as fusion. Now, we don't want it to come back together. All right, they want two things to melt together. Basically, that's what they're doing. When they blasted that thing together, they just melted it. So they had put so much into it, they're never going to get back what they put in. We're just shooting it through a Venturi, and it separates all by itself. See, the beauty of what I'm showing is the international cooperation on fusion, which is what I'm doing, fission and fusion using light, historically been close. Everybody's been close working together, because unlike nuclear fission in atomic power plants, the technology can't be weaponized. You can't take light and well, you can make lasers and stuff, but you're not going to make atomic bombs. France-based mega project also involves China, EU, India, Japan, South Korea, Russia, and the US. And I would like to tell you involve Roger as well. All right, here's what they're doing for fusion. They're taking deuterium and tritium, which are different hydrogens, and it's just one has more particles than the other one. And then they're forcing them under heat and pressure and everything else to fuse together to come out with helium, and then some extra energy and particles, which is nothing more than the heat that they put in to fuse them together. And that gives off, but it just goes crazy everywhere. So they really haven't done anything other than melted two particles together, as far as I'm concerned. It's hard for me to believe that they don't understand this. The process releases energy, yes, as heat. the total mass of the resulting single nucleus is less than the mass of the two original. Yeah, because it gave off all kinds of energy when it melted together. The leftover mass becomes energy. Exactly. This is no big mystery here. I'm just going to leave it at this. I'm telling you right now, I just showed you how we can get the byproduct of fusion, which is all that particles. And they're saying that the result announced Thursday demonstrated the ability to create fusion for 5 seconds, as longer would cause JET's copper wire magnets to overheat. ITER will be equipped with superconductor electromagnets, which will allow the process to continue for longer, hopefully longer than 300 seconds. I mean, that's crazy. And the energy they're going to put in here for those few seconds is just going to be astronomical amount of energy, and the cost of the equipment is astronomical. And how are you going to harvest that energy? How are you going to pick all that energy up? Where's it going to go to? We could squirt ours onto a solar collector, basically. It's basically almost that simple. And these are the kind of things that everything's passing through in space. I think I showed you that. But as far as I'm concerned, we just squirt it onto it, just like this thing. You have a solar collector right there. We're the same thing here. No difference. All right? I'm just going to leave it at that. I love you all. Thank you. Hopefully somebody can pay attention to this. We need this desperately. And it certainly should be looked at. And it's been avoided to look at it for many, many years now.